Right, everybody. Let's see question by question how JEE Advanced usually frames the questions. What is the language of the question, especially when it comes to stereoisomerism. See, first one, how many chiral centers are present in the following? This is relatively easy one. You can just check it out and let understand. Always check out for the uh, carbon which has four different groups. So this is one. You can see this is two. This side it is three. If anybody is confused about the third one, you need to check. This is methyl. There is one hydrogen hidden. This side it is like CH2, CHO, and CH. But this side, if you go, it is CH2, CHC. So there is a difference in either side. That's the way you need to differentiate in a cyclic structure. The same logic applies here. This is also a chiral center. This is also a chiral center. Okay. So in total, how many chiral centers do we have? So you can see total we have six chiral centers in this case. I hope this point is clear. What if there was a compound like this? I have a nitrogen here, methyl here, and I have something like an ethyl here like this with a lone pair on it. Okay. And if the question is only about chiral centers, guys, even this and this would become a chiral center. Most importantly, a three-membered nitrogen ring or a four-membered nitrogen ring with four different groups around it will also become a chiral center. So he didn't ask specifically, the question never mentioned that it is only carbon chiral centers. But the question, if it is asked how many chiral centers, you would always consider nitrogen with three-membered or a four-membered also as chiral center, not five-membered, not six-membered. Keep that in mind. Reason being, the amine inversion or the flipping of a ring can take place in five, six-membered rings, but not in three and four-membered ring. So that's why even consider this also as a chiral center. Clear? So 1, 2, 3, then 4, 5, 6, 7, 8, 9. So that would be the answer in case
So,
if it is there. Adhyatm, yes, Bacha.
so in the cyclohexane group in which you have edited the question, won't the
Mm-hmm.
carbon that's attached to the cyclohexane group, the start of the cyclohexane group, won't that be as chiral as well?
Oh, yeah, yeah. Sorry. Here also, this one also. Thank you.
Yeah.
Okay. I forgot to mention that. Even that will become a chiral center. Hmm. Clear? Right. Let's go to the next one. Examine the following structural formulas and select whether they are chiral or not. Now, if you may notice, when you have a consecutive double bonds, everybody, odd number will always give you geometrical, even number will give you optical. So odd will give you geometrical, even will give you, okay, optical. And optical means the molecule has to be chiral. Hence, you can see this is an even number with two different groups on either side, which makes it chiral. Yes, so this is chiral, everybody. Next. Although this second structure has two chiral centers, but it has a plane of symmetry passing through it. Clear? Hence, since it is optically inactive, it is a mesoform and optically inactive, it is achiral. Okay, so it is achiral. Clear? So this is not chiral form. Next, this is a chiral center because bromine, hydrogen, this side and this side are different groups. So it is a chiral center. So I'm guessing most of you should be getting this idea why it is chiral center. Next, nitrogen with a plus charge definitely acts as a chiral center considering if it has four different groups. So you can see methyl, ethyl, isopropyl, and hydrogen that makes it chiral center. And I told you, other than nitrogen, any fourth period, third period elements, if they have a lone pair also, they can act as a chiral center. So sulfur with 1, 2, 3 with a lone pair, four different groups, it's a chiral center. And here also sulfur with a lone pair, ethyl, methyl, oxygen, it's a chiral center. So these two are chiral centers as well. Next, if you may notice this one here, you need to check out whether it has something similar to that of, you know, cumulene part, that means consecutive double bond part. See, whenever you have a cyclic structure on which there is a double bond and there are two groups here and then there are two groups here, as long as they lie, I mean these chiral, these centers lie on the same line here, okay, in that case, these two groups here can be analyzed whether they can be geometrical or optical. So, in such cases, this cyclic can be, written in pseudo form as a double bond connected to another double bond, and then you have these two groups. Hence, here we have BrCl, BrCl. So it has become more like a pseudo cumulene form. So that also makes it chiral. Clear, everybody? Why? You can notice that we have even number of pi bonds. Next. You can notice this is a chiral center already, so that makes it anyway chiral for sure. Next. Last one, if you notice this particular carbon is a chiral center, hence that will also become a chiral form. So how many compounds which have been chiral? 1, 2, 3, 4, 5, 6, 7, 8. So 8 of these compounds are chiral in nature. I guess this part is clear, everybody, right?
Sir,
Yes, beta.
sir, can you tell the G part?
Yes, beta. Listen, okay. When it comes to G part, uh, if let's say this entire carbons are on this plane, okay.
Yes, sir.
If they are on this plane, can I say this carbon, if it is tetrahedral, then this group has one group has to go inside, one group has to come outside. Let's say bromine is here, chlorine is here. Is that okay? Okay.
Yes, sir.
Now, here, when it comes to this part, since these two carbons are on the same plane, and if the carbon is sp2 hybridized, the single bond should be on the same plane only.
Yes, sir.
So, in that case, can I say that if at all I take geometrically, this is the way I took it, that this is z axis, this is x axis, and y axis. So, now you notice this entire thing is on xy plane, okay, and this br is going inside z and cl is coming outside z. To agree with that, beta?
Yes, sir.
Okay, so in that case, can I say now this carbon and this carbon, these two carbons which I'm saying, they are still lying on the x axis here, correct? And
Yes,
this would be I mean the hybridization of this carbon has to be S, Px and Py. Agreed? So which means the pi bond that is present has to be towards the z-axis like this, correct? This is the way in the z-axis it should be present. Does that make sense, beta?
yes, sir.
Now, this carbon has also involved its sigma bond into x-axis and it is still sp2 carbon. So that means the other two bonds has to be on the same plane, in the y plane, xy plane. So here there is bromine, here there is chlorine. So can you notice that bromine, chlorine, these carbons, everything is lying on the one on same plane except this bromine and chlorine which are going inside and outside. Isn't it exactly how the cumulene looks like? Isn't it?
Yes, sir.
Correct. So that's why whenever you have a, you know, uh, internuclear axis on the same line here, then these groups will always be inside and outside the planes. Clear, beta?
Yes, sir.
Right. Everyone, all the cases are clear, beta? Then I can go for the next one. Right. Let's talk about the next question. If 2 is to 3 ratio racemic mixture by weight has been observed specific rotation of 16 degrees. The specific rotation of the optically pure component is x into 10 degrees, where x is how much? Okay, so we need to check out 2 is to 3 racemic mixture, 2 is to 3 racemic mixture by weight. Got it? So what does that mean? If you have 2 is to 3 racemic mixture by weight, see, when you talk about racemic mixture, I can say that uh, out of this 2 is to 3 mixture, that means if 2 by molar mass, that will be number of moles of, let's say, dextro. Let's assume that. And levo is 3 by molar mass. This is number of moles of levo. Okay. So whatever be the number of moles of dextro and levo, the difference is what you call it as enantiomeric excess. So how much is the difference here now? 3 by molecular weight minus 2 by molecular weight. So how much is that? 1 by molecular weight. So for these number of moles, right, the rotation is observed to be 16. So let's say since the levo, sorry, dextro, I can't take this as dextro, sorry, I have to take it ulta. This is levo and dextro because dextro, the overall angle is positive, that means dextro is more. So out of this 3 by molar mass should be of dextro form. So let's assume that this much is the enantiomeric excess form. Okay. So this enantiomeric excess form for these number of moles, correct? I'm getting this as 16 degrees. So the specific rotation of the pure component is how much? Okay. That is what we need to figure out. Clear? If this is 16 degrees, how much that would be? See, out of the total amount here, can I put it like this? That out of the total amount here, so total amount is how much? 2 plus 5, sorry, 2 plus 3, 5. So 5 by molecular mass, these are the number of moles. Out of this total moles, this many moles are being uh, giving 16 degrees here. Clear? So then 1 mole will give you how much here? So 1 by molecular weight, this much moles is giving out 16 degrees here. Because see, if you ask me, this 2 by molar mass and 2 by molar mass, they will cancel off with each other. Okay. So the rotation is always about the excess amount which is present. So for this much molar mass, if this is the degree which you are seeing it, then for 1 mole, how much it will be observed? Okay. Clear? So this is for 1 mole. So how much it will be observed? So it will be 16 into molecular mass. Correct. So because it will be 1 divided by this entire thing like this. Okay. Which means if you compare uh, the excess amount here, so we are checking only for pure dextro. Pure dextro means how much? See, here I'm writing in terms of molar mass. So let me write the same thing in terms of molar mass only. So if I take it for 1 gram, okay, so if I take it for 1 gram, 1 divided by molar mass is the weight that has been taken. So these are the number of moles which have been taken. So if at all I write in terms of, sorry, 1 mole here, then you can write that as 16 divided by 1 by molar mass. So this is the amount of rotation that we should get. Or if at all I put it in terms of mass, because here everything is written in terms of mass, so what I can do, see, I can say 1 gram of dextro, 1 gram of dextro, right? That is giving 16 degrees here. Okay, it is showing specific rotation of 16 degrees. But that 1 gram, because out of this 3 minus 2, 1 gram is what you will have it for dextro. Now I need to check out for pure amount of dextro. So pure amount of dextro means how much we have. Uh, check out in terms of the total mass here. So if you have, let's say this is mass ratio. So I can write it as 2 into x grams is of weight of levo and weight of dextro is 3 into x grams. This is in grams. Okay. So I can say 3x minus 2x grams here, correct? So I can say this is not 1 gram, basically it is x grams. So for x grams, so I can say it is 16 degrees. So in that case, x by molecular mass is what is giving us as 16 degrees. Correct. X by molecular mass is giving 16 degrees. So 1 mole will give you how much? So 1 mole will be 16 into molecular mass by X amount. Correct. This much will be the rotation what you will get. Now, this is what we have written in terms of moles actually, because usually the purity is being measured in terms of moles. So for 1 mole, how much that we have, isn't it? So, but we know that if you have this much amount of uh, rotation which is coming for 1 mole here, 1 mole can be also written as some weight divided by molar mass, right? And 1 mole is same as how much molar mass? 1 mole is same as the molar mass here, isn't it? So I can say that molecular weight x by molecular mass is for 16 grams. So this much will be for how much? So molecular mass into 16 divided by x by, one second, one mistake I'm making. X by molecular mass is the number of moles for 16 degrees. Oh, here this X is different. Sorry. Let me take it as some Y amount just to avoid that confusion. So Y grams of dextro. Hmm. Let me rewrite that again. See, let's say the enantiomeric excess is Y by molecular mass here. This much is the enantiomeric excess in terms of number of moles. So Y by molecular mass, this is giving 16 degrees. Then if I take it for 1 mole, how much will it give? So it has to be 16 into molecular mass divided by Y. This is the amount I should get it. Clear? Now, if you notice that uh, when it comes to racemic ratio here, um, out of 16 degrees here, 1 second. Second. So 1/5 of the part is 16 degrees. So I can write it this way. 1/5 is in 16 degrees. So one part will be 80 degrees. Oh, right. Sorry. Let me put it the other way around better to make it much more easier. See, you can take it. Weight of dextro is 3y. Weight of levo is 2y. So enantiomeric excess weight will be equal to 3y minus 2y. Now that is equal to y. Can I say that the total amount of the mixture is 5y, out of which y is the excess amount which you have. So that means the uh, part of dextro, part of dextro which gives rotation, parts of dextro which gives rotation is y divided by 5y. How much? 1/5 of the dextro part is giving the rotation of 16 degrees. So I can say if 1 by 5th part is giving 16 degrees, then one part of dextro, which is pure form, one part means only dextro, will give you how much? So that makes it 16 divided by 1 by 5, which is equal to 80 degrees. So that means the pure dextro form is how much? 80 degrees. And pure levo form is minus 80 degrees. So in that case, if at all I have to write that 80 in terms of x into 10. So x into 10, that is equal to 80. So x is equal to how much? 8. Clear everybody? So you can, instead of writing everything in terms of molar mass or writing in terms of number of moles, I can simply write in terms of parts. That makes it much more simpler. So you can see 1/5 of the part in the solution, only 1/5 is the pure form, and that part is giving 16 degrees. So one part which is a pure form should give you how much? Clear? Everyone, please do check. See, the other way around, the questions can be framed here is in percentages. So sometimes it will be given like 20 is to 80 percentage of racemic mixture, like this. So again, you do the same thing. So 60 divided by 100 is the part which will give you certain amount of specific rotation. So, and in that case, if you take 100 part of that, then how much will be the rotation? Okay. Clear, everyone? Right. Let's come to the next one. How many of the following are more acidic than acetic acid? Okay. This one is more from GOC part. So as of now, I can just simply give the answer directly. See, any withdrawing group, one, here also OH is withdrawing group. And you know that benzoic acid is slightly more, less acidic than more acidic than acetic acid. And this one is also withdrawing group. So how many we have? Four of them are strongly, sufficiently withdrawing by minus I, which makes it more acidic. Next. Let's see. Total number of stereoisomers for this compound is how many? Okay. Let me copy this here. Total number of stereoisomers for this one. See, we have CH3, then we have CH, uh, we have here as CHD here, clear? Like that, we have how many? Total of three such groups we have. So CH, then we have CHD with CH3, and another CHD with CH3. Correct? Everybody, check into these cases. So I hope all of you got the structure, how it looks like. Now, have you noticed that here we have a chiral center 1, 2, and 3. These three are the chiral centers. Correct? Now is a problem here, because with respect to this carbon here, it is a tetrahedral structure like this. Tetrahedral structures, this is tetrahedral structure like this. So here, whatever the carbon's configuration is, here and here, see, this is hydrogen. So we forget about those, that hydrogen part. But here is one chiral center with four different groups. Here is one chiral center with four different groups. Here is with four different groups. Okay. If this has R and S configuration, and this has R and S configuration, and this has R and S configuration, this carbon can never be a chiral center for sure. But with respect to this, when you have this as R and S configuration, that might be superimposed if you have same R and S here also. Got it? So which are all the cases where you can have non-superimposability? So check out. When you have non-superimposability, I'll tell you. Let me take this and copy and show you in which cases it will not. So first case, when this is R, this is R, and this is R, and its mirror image. When this is S, this is S, this is S. These two are mirror images of each other. Next. Now, when this is R, this is S, and let's say this is R. Okay. Now, if I take a mirror, if I take the mirror image of this one, so I will have, you know, I'll have this as S, R, and S. These are the four cases I have. Now, what might come into our mind is that, sir, what about having, let's say, RSS here and write a mirror image as uh, SRR? Now, see the problem. Okay. SSR here, I have already written SSR. These two are superimposable. Why, because the distance between these two and these two are same, and the tetrahedral, all the distance will be same. So you can never differentiate that these two are different. Similarly, you cannot differentiate these two are different. Are you getting the point, everybody? So therefore, these two are not something which we are writing it as new. So maximum how many we can get? 1, 2, 3, and 4. These are only the four unique ones which you can get, which are stereoisomers. So how many we can get? 4. Clear? Any doubt in this question? Rest all, any combinations you make, they will always be repetitive. Right. See the next one. For this, if at all I perform a monochlorination and that gives X number of isomeric products, which on fractional distillation give Y number of isomeric products, find the value of X minus 2Y. So let's see. This is a compound we have. So for this case, you have to do monochlorination. So I'll just copy as many structures as possible so that I can write the structural form of it. Then we can see how many we can get stereo-wise also. So first, starting with one chlorine here, one chlorine here, one chlorine here, one chlorine here, and one chlorine here, one chlorine here, and then you have one chlorine here. Correct? Structurally, I have covered all the positions, if you may notice. Clear? So you can see 1, 2, 3, 4, 5, 6. So 1, 2, 1, 2, 3, 4, 5, 6. And then we have this methyl group. Okay. Structurally, these are all the ones which are covered. Now, fractional distillation gives Y number of isomeric products. So see, here, the minute the chlorine comes into picture, whether chlorine is there or not, you will see that we have a chiral center here. Similarly, now we have two chiral centers here. Here also I have two chiral centers. Here I have one chiral center. Here again I have two chiral centers. Correct? Here I have one chiral center. Here I have one chiral center. So if you count the total numbers here, so 2, 4, 4, 2, 4, 2, and 2. Okay? 10 plus 2, 12, 12 plus 4, 16, plus 2, 18, plus 2, 20. So total how many? Number of stereoisomers we have is 20. Everyone clear? Now you know that by fractional distillation we cannot separate the enantiomers. We cannot separate enantiomers. So here, out of these two here, you know that only one can come out as the fraction. So one fraction. Out of four, I can get two. Here, out of four, I can get only two fractions because enantiomers cannot be separated. There are two enantiomeric pairs there. Here also, I'll get one. Here, I'll get two. Here, I'll get one. Here, I'll get one. 2, 3, 5, 6, 7, 8, 9, 10. So how many we have? Fractions. Number of fractions we get is 10. So 20 minus 20. What is the answer? 0. Everyone clear how to solve these cases? Next. Check out 27. How many of the statements are correct? Trans-cyclooctane is chiral due to the presence of chiral or stereo axis, which is true. What does that mean? Let me explain. Okay. So basically, if you have count the number of carbons 1, 2, 3, 4, 5, 6, 7, 8. Okay. And on this 8, if at all I make a double bond here like this. Now, this is one particular structural basis on which you can put double bond there or you can put double bond here also like this. Correct? So here you can see this will become a trans cycloocta octane. Okay. Now you will not find any kind of symmetry here, neither a plane of symmetry nor a center of symmetry or anything. Okay. What do you mean by chiral axis? Chiral axis is any particular axis like this. If you notice, with respect to this double bond here, correct? If at all I draw this axis like this, let's say this is that axis. Okay, across which you will not find any kind of symmetry, correct? Neither you will find any plane of symmetry, neither center of symmetry or anything. For example, if you have C double bond C double bond C, here I have, let's say, methyl and hydrogen, and here if the methyl goes in and hydrogen comes out. In such case also, this particular axis, this is also called as chiral axis. Across this chiral axis, right? That means on this particular line, if at all I draw this particular line, I can consider this entire thing as one bunch, as one particular uh, spot across which I have four groups like this: methyl, hydrogen, methyl, hydrogen. But there is no plane of symmetry around it. Such a particular axis is what we call it as the chiral axis. So you can see trans-cyclooctane has a chiral axis. Here also there is a chiral axis. There is no symmetry which you will find across it. So yes, this one is true. Bulkiness order at ortho positions in biphenyl system gives in this particular order. Okay. So what does that mean? See, if you have these two groups here like this is biphenyl. On biphenyl, let's say I have different groups here like this at ortho positions. Correct? And the question here is, what if you have any of these cases? Okay. See, what I'm trying to say is if you have all bromines here, correct. So if you have bromine, 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 and bromine, of course, there will be repulsion because of those bromines. Van der Waals repulsions will be there. So what happens here? One phenyl will be coming out of the plane like this, and one phenyl will be on the plane like this way. Clear? And this bromine will go inside, and this bromine will come outside, while other two bromines will be on the same plane like this way. Okay. And because of which you will not have any plane of symmetry. Of course, here not two bromines, sorry, one should be hydrogen so that they can show the optical isomerism here. So one is hydrogen like this. Okay. If you have it this way, now there is no plane of symmetry, no center of symmetry anywhere. Hence, this molecule will become chiral. Now the question asked is, between bromine and bromine, do we have more repulsion? See what happens here is like this. Biphenyl should be like this. Because of the repulsion, they'll keep going up like this, and try to be always here. When they come down here, again, it will come up this way. It will keep on moving across one plane so that it will always try to be permanent this way, not this way. That means they will not be on the same plane. They'll try to be on the opposite, perpendicular plane to each other. Now that depends upon how much strong repulsion they will give. Bromine relatively will give you more repulsions than methyl, chlorine, nitrogen. This is what we need to say. See, problem here is CH3 is a three-dimensional molecule completely, while bromine is just an atom. So if you compare, uh, if you compare in terms of bulkiness, CH3 will offer the most bulkiness here. Then comes NO2, then comes bromine, and then comes Cl. So this is the correct order. So hence, this statement is not true. Okay. I guess this part is clear. Next. If you notice this next one here, we have a chair form here with on axial position we have OH and on equatorial position here we have methyl group. Okay. Now notice this is not a chiral center. This is not a chiral center. So we need to check out structurally do we have any plane of symmetry or not. Answer is yes, because I can pass a plane through this, OH, this one here like this. This entire thing will become one plane. So that plane will divide this, chair into two parts of it. Clear? So, or you can put it like this in this structure. Okay, obviously it's difficult to view from that angle here. So I can say here OH is coming out of the plane, and this one is methyl is also like this. Okay, now you can see this way there will be one plane of symmetry that will in that plane you will not have, I mean, you will be seeing any symmetry on that. So therefore this will not be optically active. Clear? Next. Here, this is a meso compound due to plane of symmetry. Answer is this is not even a chiral center. This is not even a chiral center. So it is not even meso. So this is not the correct question of. So for meso to be present, first we need to have a chiral centers. But along with the chiral center, we need to have a plane of symmetry. Is that clear? Check out. Find the number of incorrect statements. Mesotartaric acid has a different melting point than tartaric acid. See, when it comes to mesotartaric acid, this is the structure OH, COOH, H, OH, H, and COOH. And let's say if we have dextro form of tartaric acid, I'm just assuming the OH is on the right, one OH is on the left here, like this. Now, are these two mirror images of each other? No. What are these two? These two are diastereomers. And you know that diastereomers will always have different melting points. So yes, different melting point and different boiling point. So statement wise, this is correct. It's not our answer, but statement wise, it is correct. Next. You notice that this line, this is a single bond here, single bond here. So when you have a single bond, you can rotate easily. So here and here, rotation is easy. And if you notice that their form here, it is like an anti-molecule. Here it is like a eclipsed form. That means it is like a staggered form. Here it is like a eclipsed form. So what do we call it? We can call it as a conformational diastereomer. Diastereomers because they are not mirror images of each other, but they are conformational based. So yes, this is also a correct statement. Next. Here, for this case, it is optically active model. We need to check out it is optically active. So very interesting case, this one. You notice here carefully, we have like this with nitrogen, nitrogen, then, sorry, this way with a double bond O here and a double bond O here. And then we have a hydrogen here, methyl here, and a methyl here, hydrogen here. Now from this particular position here, if you start moving towards methyl and go opposite to the methyl here, similarly if I go on the same distance H here, you will get another H here. If you go to oxygen at the same distance of X, you will get oxygen. If you go to nitrogen, you will get nitrogen. So what are we exactly finding out? Actually, we find a center of symmetry. So when a molecule possesses center of symmetry, will it be optically active? No. So this statement is incorrect. Okay. So it says that the molecule is optically active, but it is not because it possesses center of symmetry. Clear? It may not possess plane of symmetry, but it does have a center of symmetry. Next. This molecule has chiral center and shows optical activity. Okay. So you can see, yes, here there is an chiral center, correct, and it shows optical activity. So this statement is also correct. Okay, so out of the given statements, if you notice, only one statement is correct. Sorry. How many? One, two, optically active. This is also correct. This is also correct. Yeah, all of these four are correct statements in this case. So what are the incorrect statements? Zero. Clear, everybody? Right. Let's come to the next one. Which of the following are not meso compounds? Now you need to figure out whether they are meso compounds or not. Let's notice. How do we judge their meso nature? See, whenever your structure is given, my suggestion is always try to draw uh, the eclipsed form of it. That makes it much more easier. Here, for such cases, everybody, my recommendation is always go for Sawhorse projections. So check out. So Sawhorse projection is draw this line, keep it up, down, whatever the original lines are given. The other two lines, you make it like this. So now write all the structures which are present, methyl and methyl, hydrogen and chlorine, hydrogen and chlorine. So this becomes the Sawhorse projection. Likewise, here also I'm drawing the Sawhorse projection, H and H. Then I have two groups, chlorine and ethyl. Here I have chlorine and methyl. Likewise, here also I'll draw ethyl, ethyl and methyl. Then I have chlorine and hydrogen. And here I have hydrogen and chlorine. This is the Sawhorse projection. Last one, two chlorines, hydrogen and methyl. methyl and hydrogen. This is the way I have drawn it. Okay. Now I'll take one structure here and try to write its uh, eclipsed form. So check out. So here like this, I'll keep these two intact. This methyl also intact here. Now only thing on the right hand side, I have to rotate it so that the methyl comes down here and these two groups will go up. So hydrogen will be opposite here. Got it? On the same side. And chlorine will come on this side. Okay, as you rotate, this is what you will get. So everything which is here hydrogen was going inside, now hydrogen will come outside. Okay, and chlorine was coming outside, now chlorine will go inside, like this. Okay, now if you make it stand here, if you make it stand here, correct, notice it. Now I'll make it stand here like this. You can stand it like this here. And once you make it stand, you can watch the molecule and try to draw its Fisher projection. And as you draw its Fisher projection, you will notice that we have methyl up, methyl down, chlorine right, hydrogen right. And here hydrogen left, chlorine left. Clear? Now tell me, is this a mesoform? No, because there is no plane of symmetry passing. That's how you need to judge it every cases. Okay. Over the time you can just watch the structure and understand that easily, but unless you start learning how to draw it, you become very comfortable, it becomes difficult to assess it. So initial days when you are trying it for the first time, my suggestion is always try to draw it and check one by one. Okay, so sorry. One second. It's not coming out, so I'll draw it here only. So in this case, if you check out this molecule here, so again I'll write it like this. So hydrogen would be here. Methyl chlorine is already here. Now as you rotate, chlorine will come here, ethyl will come here. Correct? So now if at all I make it into Fisher projection, I'll have hydrogen here. Okay. Methyl and ethyl here, chlorine and chlorine here. So this is nowhere meso. So this is not meso at all. Because one side we have ethyl, the other side we have methyl. So there cannot be plane of symmetry here. Next case. Option C case here. Notice I can draw it like this. Here I can have methyl and ethyl. The problem is the same here also. So I can have hydrogen here, chlorine here. So if I draw the Fisher projection, I'll get methyl here, ethyl here. Although I can get chlorine and hydrogen on the same side, problem is this is not a plane of symmetry because methyl and ethyl here, these two are different groups. Hence, this is not even meso. Last one. So you can see here you have hydrogen and methyl here, chlorine here, and now chlorine will come here, and then hydrogen and methyl will come here. So as you push it onto the Fisher projection here, I can have two methyls on the left and two hydrogens on the left. Here we can clearly notice that there is a plane of symmetry passing through it. Hence, it is a mesoform. So what are the correct answers here? A, B, C. In all A, B, C, we do not have mesoform. Only mesoform is observed in D. Anyone has a doubt? Please do ask right now. Did you get this?
Yes.
Pratisha? Did you understand this? How to
Yes, sir.
write the mesoforms? Very good.
Yes.
Sudiksha,
Yes, sir.
Tanish,
Yes, sir.
let's go to the next one. Which of the following has zero dipole moment? Okay. If the vector sum has if the vector sum is getting cancelled, then we have zero dipole moment. Unfortunately, here there are two vectors coming on the same side directions here, like this. Chlorine and chlorine are present on the same direction. They are not getting cancelled. So mu is non-zero. Here also, chlorine and chlorine like going like this. So mu is non-zero. Now here all three chlorines are going upwards, which means they are all going on to the same direction. So mu is non-zero. Now here one chlorine is going like this, the other chlorine is going like this. So mu is zero. So compounds having zero dipole moment, only one of them, which is D. Clear? Next. In the following structure, find the correct statements. Statement 2 is a mesoform. Statement 1 and I mean structures 1 and 2 are diastereomers. 3 and 4 are diastereomers, or 1 and 4 are enantiomers. Okay. Just now I told you the technique. What to use? We can just simply use the Sawhorse projections and resolve these kind of cases. So let me do that here. So let me take these four structures. Yeah, in these four structures, if you notice, the first one, I can write it like this. Whatever the structure that is given, you write down that first. Then we have bromine, hydrogen, methyl with hydrogen, OH, and methyl. This is the Sawhorse projection. Second case, COOH, COOH here. I have H and OH. Here I have OH and H. Third case, I have methyl and methyl, H and Br, H and OH. And last case we have methyl and methyl, OH and H, H and Br. These are the structures. What do we have? Clear? So I'll give some space to write and judge how they are looking with each other. Okay. So first thing what we have to do, we have to write the eclipsed form of it. So I'm writing it like this. Methyl, methyl on the same direction. Bromine and H. Here I have OH and H. Done. Same way here. COOH, COOH, H and OH here, H and OH here. Next. Methyl and methyl here, H and Br here, OH and H here. Lastly, we have methyl and methyl here, like this. Methyl and methyl here, correct. I'm keeping this H here, OH here, H here, Br here. So these are all the eclipsed form, everybody. Now, having the eclipsed form, now I can write the Fisher projection. So I can write methyl here and methyl here. And if I watch it from the bottom side, then bromine will be on the left, OH will be on the left, H will be on the right, H will be on the right. Likewise, here, if you write the Fisher projection, COOH up, COH down here. So H and H will be here, OH and OH will be here, which is the mesoform. Next. Here, methyl and methyl here, H and OH will be on the left, Br and H will be on the right. Last. Here, methyl and methyl will be here, H and H here, OH and Br here. These are the four forms we got, everyone. Now we got to analyze this, this structure and this structure. Okay. So in the second structure, we got an idea that this is mesoform. Okay. And if you notice these two, well, this is 1, 2, 3, and 4. So you can notice that between 1 and 2, only at one position the chirality has changed, which means 1 and 3 are diastereomers. So these two are diastereomers. While here, this group with any of that, if you compare, they are still going to be diastereomers only. Okay, so methyl, methyl, bromine and OH are on the same side here, but they are not. That is diastereomer with all of them. It is not the same. Okay, now go to the options and let me pull these options also and see which of them is more appropriate. Oh, sorry. 1 and 4 looks exactly same. My mistake. 1 and 4 are just the opposite in terms of mirror image. Correct. So 1 and 4 are enantiomers. So yes, this option is correct. 3 and 4 makes it diastereomer, which is correct. 1 and 3 are diastereomers, which is correct. 2 is meso, correct. All of them are correct. Please notice. Everyone, please check. Very good question. You know, this has to be learned thoroughly. If any problem, I mean, if you're still getting any confusion or issue in terms of writing anything, please let me know. All good? Right. Let's see the 32nd one. Plane of symmetry is present in which of the following in all of these cases? Right. So let's see. The first case, I'll answer it here itself. You have H and fluorine here and methyl and hydrogen here. Okay. Now, in case if at all I take a plane which is passing through these four, correct? If at all I take this as passing through these four, through the center of this one, so definitely these two will be mirror images of each other. That means it has a plane of symmetry. So A has plane of symmetry. Are you all getting the point? How to notice that? Right. Next. B. 2R3S23-dichlorobutane. Okay, now very interesting one. So if you have like this, everybody have methyl, methyl, H and H, Cl and Cl. Everybody, notice this. How I've written it structure directly, I'll tell you. Now start with the configuration. This will be 1, this will be 2, this will be 3, this will be 4. These are the priorities with respect to this chiral center. Notice how 1, 2, 3 is rotating. 1, 2, 3 going clockwise. Okay. Clockwise means S configuration in this case because the least priority is on the horizontal line. Next. Now I'll remove these cases. Again, let me rewrite for the second chiral center. So priority wise, this is 1, this is 2, this is 3, this is 4. Now notice 1, 2, 3, it is going anti-clockwise. So which means it has to be R configured. Yeah. Have you noticed something? Whenever there is a mesoform, everybody, if the top one is R, the bottom will always be S and vice versa. Okay. So which means whether you take S and R or whether you take R and S, it doesn't matter because mesomers are identical. They are superimposable. So whether I write it this way or whether I write it in this manner, these two are superimposable. Cl, Cl, H, methyl and methyl. These two are superimposable. So everyone. So whenever one chiral center, I mean symmetrical kind of molecules, when you notice, if you have one chiral center being R, the other one being S, or one is S and one is R, it has to be mesoform. So mesoform will have a plane of symmetry. And if that's the question, yes, answer is yes, it has a plane of symmetry. Next one. In case number 3 here, if you notice, if you try to check out only plane of symmetry, notice this carefully. Here, if at all I write down one line here like this, you can see C and C will become mirror images. This chlorine and chlorine will become mirror images. Yes, so that means with respect to this particular line, I'm noticing that there is a plane of symmetry. Answer is yes, here there is a plane of symmetry. Correct. Last one, a carbon having, one hydrogen with 3 phenyl groups here like this way. Okay. The question is, does this have a plane of symmetry or not? Okay. Now, problem what happens is I told you about this. When you have carbon with 3 phenyl groups so close to each other, now if one phenyl is in this way and the other one is, let's say, the back side like this, okay, and the other one is coming in the front side like this, and then we have H. Now, in case if at all I try to make any plane here, let's say one passing through hydrogen like this is the plane I took it. This is the plane I took it, and I'm trying to observe that these two will be, mirror images of each other. Unfortunately, because of their steric factors, these two will always have some angle change. That is called a propeller shape. So it will have some propellarity here by which it will avoid having, you know, existing in the same plane or just like mirror images. So hence, this will not have any plane of symmetry. Okay, due to adaptation of propeller shape, it cannot have a plane of symmetry there. Everybody, 32 is clear? Next. Which of the following pairs of compounds are not pair of enantiomers? Very, very important question. Very standard one. And this is asked in JEE Advanced quite a number of times. Check out how we need to judge. So the following pairs are not pair of enantiomers. So in such case, my request is always check out if you keep the structure in a very similar way. Let's say here bromine is coming out of the, inside the plane, chlorine is coming out of the plane. Try to put the second structure very similar to this skeleton. To do that, what I need to do? First, I need to hold on to this plane and rotate it by 180 degrees. Then it will rotate around like this. And now the bromine will come on to the left hand side here. But it will not stay outside, it will go inside. This is how the bromine will be. And the chlorine will come outside. So which means this compound 1 and 2 look exactly same. So these are identical. Okay. Apply the same logic to this side also. Here, the structure is already, here we don't have to make any rotation. One group is coming like this, the other group is going here. And in the second case, you will notice one group is like this and the other group is going like this. So if I take exactly the way it is and try to come and try to superimpose, will it superimpose here? No, it will not be able to superimpose here, which means, and does it have a plane of symmetry? No, this is not a plane of symmetry. Does it have center of symmetry? No, which means it is chiral. If this is chiral, and both of them are non-superimposable, these two are mirror images of each other. So in cyclic structure, everybody keep the same structure, same skeleton on the side and check out the one which is going in should come out, one which is outside will go in. If such is the case, then these are pair of enantiomers. So yes, B is a pair of enantiomers. Next, third one. Third one, unfortunately, they look like mirror images. In fact, there are mirror images, but unfortunately, there is a plane of symmetry passing through it, which means you can superimpose these two. So what are these two? These two are mesoforms and not enantiomers. And last case, again, it is exactly same given here, correct? So if you notice structure by structure here, you can see this molecule, if at all I try to put it here, this chlorine will superimpose, this chlorine will superimpose, but these two chlorines will not superimpose. Okay, which clearly suggests that means this might have, here there is no plane of symmetry. That means there is some chirality on this carbon here, correct? But are these two enantiomers? No, they are not enantiomers of each other. All right, they are not enantiomers of each other. Hence, what are these two? Diastereomers, because they are not mirror images. So which of the following pair are not enantiomers? That was a question. Okay, so which one is that? A, C, and D. I hope all of you understood how to judge these cases. Yeah, right. Next, check out 34. S-malic acid is at a concentration of 5 gram per ml in 10 centimeter polarimeter, given absorbed rotation of 75 degrees at 25 degrees Celsius. What is the specific rotation of S-malic acid? So you know that angle theta will be equal to alpha, which is the specific rotation, into C into L. So what will be the alpha value here? So that will be equal to theta, which is 75 degrees, divided by concentration, which is 5. Okay, now observe it carefully. It is given 5 gram per, 5 gram per ml. You know that 1 ml contains 5 grams. So 1 liter will contain how many, how much amount of concentration in this case? Okay, because we have to write the concentration in gram per liter. Okay, so therefore, for 1 liter means 1000 here, correct? So that makes it 5000. So we are talking about 5000 grams per liter here. So you need to divide it by 5000 into length should be in decimeter cube. So it is 1 dm. So this is what you need to write. Clear? So this will become the concentration. This will become the decimeter part of it. So what is the alpha value here? So if at all I cancel this off, it will go for 25. So 25 into 10 raised to power of minus 3. This is what we should get. Clear? So what is the specific rotation? Specific rotation, is it greater than 50? Definitely not. Is it greater than 25? Definitely not. Is it less than 25? Yes. Is it less than 10 degrees? Yes. Okay. Clear? Next. Check out on 35. Again, a very interesting case. You have to apply CIP rules on this case, but first we need to assign the uh, IUPAC numbering. So check out. As per IUPAC numbering, here there are two chlorides, here there is one chloride, here there is one chloride. So which means definitely the numbering should start from here: 1, 2, 3, 4, 5. This is how the numbering should be. All right. That makes there is a chiral center at second position and there is a chiral center at fourth position. So let's start with the second one. So such kind of cases, everybody, what you do, you write the structure the way it is, like a single bond. I mean, with a open chain, like this. This is the way it is. Chlorine is coming out of the plane. Hydrogen is going inside the plane. This is carbon 3. This is carbon 1. This is carbon 2. All good? Now, as per now you need to watch the molecule such a way you can put the Fisher projection. And you know that as per Fisher projection, the vertical line group should be moving away from you, and horizontal one should be pointing towards you. So, and that's what we have done here. So this is carbon 3 here, this is carbon 1 here, and uh, you can see when you watch it from here, chlorine will be on the left, H will be on the right. Now let's give the uh, ranking based on CIP rules. So chlorine will always get the first priority, and carbon 1 has two chlorine, so that means it will get second priority. Carbon 3 is third priority, and this is fourth priority. So how is it rotating? 1, 2, 3. It is going anti-clockwise direction. Anti-clockwise direction makes it R configured. That will make it R configured. Okay. So on second position, we have R configuration. Now let's do the same thing at the fourth position. So put the structure same way the way it is. Like this it is there. And then hydrogen is coming out of the plane and chlorine is going inside the plane. Okay. Hydrogen is going outside the plane and this one. So when you watch it from this end, everybody, considering this carbon 3 is the head, carbon 5 is the foot. In that case, if I write the configuration, if I write the Fisher projection here, C3 and C5, you will notice the hydrogen is coming towards the right, chlorine is going towards the left. Now again, give you the a priority here. So the first priority is definitely going to be carbon, right? And then you notice on this side, there is CH2. Here also it is CH2. Then there is carbon with two chlorines. Here there is carbon with one chlorine. So which one is more prioritized? Carbon 5 is more prioritized. So this is 2, this is 3, and this goes 4. So how is 1, 2, 3 rotating? It is going anti-clockwise direction, which means this has to be S configured. So what is the answer, everybody? So it has to be 2R and 4S. So which are the correct options? A and D. Please check out thoroughly, everyone. If there is any kind of doubt in this question, please you can ask me back. Sorry. It is anti-clockwise. Sorry. I'm getting anti-clockwise. Anti-clockwise means R. 4R. Yeah. Made that mistake here. So it should be C. Can we go ahead? Right. Check out on 36. 36 is basically an alene form. So C, triple bond C, triple bond C. You have A and B here, A and B here. A and B are non-stereogenic different, ligands, right? And are optically active due to. Okay. So you can see when it comes to optical activity, it is based on what, is it having a chiral center? No. Is it having a chiral plane? No. Is it having a chiral helix? No. What it has is chiral axis. I told you that on this axis. See, what do you mean by axis is like this? You have to take an axis on which you have to collate all the carbons. You collate all these carbons and make it into a dot like this. And on that dot, notice if there is any plane of symmetry or center of symmetry coming across. You can notice that A is going coming out of the plane. Here B is going inside the plane, while on the other hand A is here and B is here. So now notice, is there any plane of symmetry? No. Is there any center of symmetry? No. So that kind of an axis is called as chiral axis. Okay. So it is because of that chiral axis we will show that it is optically active. Next. Notice on 37. Structure of S2-fluorobutane. So we need to check out whether there is S configuration or not. If I give you this kind of structure, can I say it is S configuration or R configuration? We can't say it because this is not a structural, this is not a structural representation which will show us the configuration. Got it? Whether it is a correct configuration or not. So this cannot be judged at all. This is given with a three-dimensional structure, so we can judge it. So here you can see the structure carefully. This is how it is aligned. So fluorine, hydrogen, methyl is going in, ethyl is coming out, everybody. So you have to watch the molecule from this angle so that you can write the Fisher projection this way. Fluorine, hydrogen, ethyl will be on the right, methyl will be on the left. Now notice the put the CIP rules 1, 2, 3 and 4. So how is 1, 2, 3 going? 1, 2, 3 going clockwise with least priority on the vertical line, which makes it R. So, but we need S. So this is not correct. So go for the second one. So here, if you notice, again, I have group here, H here, fluorine here, methyl is going left, ethyl is going right. So priority wise, 1, 2, and 3. So this is going anti-clockwise direction, which means it is S configured. Yes, so one option we got it correct. Last one, 1, 2, and 3 and 4. So you can see 1, 2, 3 is going anti-clockwise direction. That means it is R because the least priority is on the horizontal line. So only one option is correct, which is C. Everyone, please check it out. Right. Next. Which are the following methods of optical resolution? See, for resolution, we use crystallization, we use chromatography, we use diastereomeric complex formation. We cannot use fractional distillation because fractional distillation cannot separate enantiomers, while A, C, and D can be used for enantiomeric separation. Okay. Next. 39. Match the following, and we need to check which one is more appropriate in this case. Check out. First one. If hydrogen and hydrogen are on the same side, it is definitely going to be, cis molecule here. And second thing, this carbon has 4 different groups. That means it is a chiral center, so which makes it optically active. So what are all the correct options? P, optically active is correct. Second, there is no plane of symmetry. Number of chiral centers is 1, which means S is correct. Number of stereo centers. Have you noticed that this is this carbon, and this carbon? All three together are stereo centers. So here answer given is, here the option given is 2, that is not correct. So only P and S are correct in this case. Second case. This is a chiral center, this is a chiral center, and there is no plane of symmetry here. Hence, it makes it optically active. So P is correct again. And plane of symmetry is not there. Number of chiral centers are 2. Stereo centers are 2. So yes, P and T is correct. Now there is only one chiral center and that is optically active. So P is correct. There is no plane of symmetry. S is correct. So these two are correct options. D. Now notice that there is a plane of symmetry here, plane of symmetry here. Correct. and chlorine are on the same side here, so therefore it is a cis molecule, so it is optically inactive, so Q is correct. So there is a plane of symmetry, R is correct, and number of stereo centers, geometrical centers are also stereo centers, so there are two stereo centers, so QRT, these are the correct options. Please check everyone. Is 39 clear? Next. Check out these cases. We need to find out the total number of stereoisomers in this case. So first, this carbon is a chiral center. Then a double bonded system is a unit. And there is one more chiral center like this. Okay. But you notice this carefully because there is a plane of symmetry that it can come across. And you know that when you have a plane of symmetry, what is the formula to be used? 2 raised to power of n minus 1 plus 2 raised to power of p minus 1. And if p is odd number, then we will use n plus 1 by 2. So use this formula here. 2 raised to power of 3 minus 1 plus 2 raised to power of, this is 3 stereogenic centers, units. So you'll have p is equal to 2, so 2 minus 1. So total 6. So how many total number of isomers we can have? 6. So answer matching is R. Clear? Next, when you have this kind of cyclic cases, everybody, I would suggest you simply write down the structures and see whether there is any uh, similarities coming. First, all methyls all methyls going up. That is one way. One methyl going up, other two coming down. Correct? And no matter whatever, because the distance is same, no matter whatever else you try, it will be repetitive structure and superimposable. So that means if you try these two and like this is one and the same, these two are again the same, because this one gets superimposable with these two. Okay, so which means maximum, how many number we can have? Only two. Next, we have one here we can have cis and trans, here we can have cis and trans. Now, left hand side, right hand side groups are different, so there is no symmetry. So simply you will add 2 raised to power of 2, so 4. So answer is Q. Last, here we have 1 and 2. Again, there is no symmetry on either side, so 2 raised to power of 2. Again, answer is 4. Right? Sorry, what about this one? Yeah, here I think it should is missing. This should have been CH2 beta. Yeah, now it's fine. So again, Q. Is the answers we got R, P, Q, Q. Everyone clear with that? See this next question. Identify the structure that represents a conformation of 2,2-dimethyl butane sighting along carbon-carbon bond. Okay. So which means you can take any carbon-carbon bond and try to make a conformation out of it. Okay. So you can take carbon 1,2, carbon 2,3, carbon 3,4, and you can make a conformation. Got it? So, in such cases, my suggestion is try to do the reverse one. So first you take the uh, Newman projection and try to write it into the respective Sawhorse projection. So check out what I can do. Here I'll try that. Here what do we have? Like this, and this is being connected to back side this way. So front side we have methyl, hydrogen. Back side I have hydrogen, methyl and methyl. Do you see any similarities here? Do you have something like 1, 2, 3, 4 carbons with two methyl groups? 1, 2, 3, 4 carbons, but two methyl groups are on the same position. So this is not the correct conformation for the, I mean, this is not the correct conformation for this structure. So P is not. Everyone clear how to do that cases? Yeah. Next, check out the next one here. See, after that, I'll write this Q1. So I have hydrogen, hydrogen, hydrogen. So basically methyl connected to backside with methyl, methyl and ethyl. Ethyl, you write it like this. Okay. So now can I write this as 1, 2, 3, 4 carbons having two methyl groups? Yes, that is what exactly it is. 1, 2, 3, 4 carbons having two methyl groups. So yes, this structure is correct. Next, R1. You have tert-butyl here like this. Tert-butyl means this carbon has three more carbons to it. 1, 2, 3 carbons to it. Hydrogen, hydrogen is present here. Backside, I have all three hydrogens again. Hydrogen, hydrogen, hydrogen. Okay. Isn't it the same thing again? You see 1, 2, 3, 4 having two methyl groups. See, yes, this structure is also correct. This is also correct confirmation. This conformation is on the basis of 3 and 4 carbons. So you can see 3 and 4 carbons. If this is front carbon, this is back carbon, you will get this one. Next, last one, we have like this hydrogen, hydrogen, methyl, and backside I have methyl, methyl, and hydrogen. Okay. Again, you notice that 1, 2, 3 carbons having, sorry, 4 carbons. How many carbons we have? 1, 2, 3, 4, 5. Yeah. So we have 1, 2, 3, 4 carbons with one methyl group. That's not how it is, right? So there are supposed to be one more methyl group on it. Clear? So this is not correct. Does this look exactly same? One second. This carbon has two methyl groups on it. Yeah. One more hydrogen is missing out here. Correct? Because this is CH2 and methyl. Yeah. One more methyl is missing. So this is not even a correct representation. So wrong. So what are the options here? Q and R. So which is C and D. Clear? It works easily when you go the backward side. Next. Which of the following pairs of compounds are correct notation given? Yeah. So first one, Z means on the same side, E means on the opposite side, correct? So we learned that already. So you can see here, phenyl and phenyl are priorities and both of them are on the same side. So that means it is a Z isomer. Here it is 1 and 1, so it is E isomer. So E azobenzene and E azobenzene. This is correct. Okay, one second. Next, check out B part here. In the case of B part also, you need to emphasize based on how the OH and CH3 groups are, because those are the priority groups. So this is 1 and 1. How are they? Opposite to each other. So E. How are these two? On the same side. So Z. So this one is also correct representation. It is acetyl oxide and both of them are correct. Next one. Here COOH and phenyl are opposite to each other. But hydrogen, hydrogen are a common group. If common groups are opposite to each other, that is called trans. Yeah, that is called trans here. So here it is trans given. So that is correct. Last one. You have common group. Now you have to assign Z and E isomer. So you can see this is high priority group. Here this is high priority group. Both of them are on the same side. So if they are same side, it is Z isomer. Clear? So we need to always check out based on high priority groups. Correct? Next, if you notice here, uh, between these two, high priority group is bromine, here it is chlorine, and between these two, high priority group is 1 and 2. So both of them are on the same side, so it should have been Z isomer. So, but it is given E isomer, so this is wrong. So A, B, C are correct in this case. Everyone clear? Next. Check out which statements are correct regarding these cases. So if chlorine are on the same side, this is uh, trans isomer, as well as high priority groups are opposite, so that makes it E isomer. Here it is cis isomer and high priority groups are on the same side, so it is Z isomer. Now go back and check the options. These are geometrical isomers. True. They are diastereomers. True. One is E, second one is Z. True. Their confirmations wrong. So A, B, C are correct in this case. Next. Which of the compounds shown below are isomers? Okay. Now, he didn't specify what type of isomers. In such cases, my suggestion is always check out the DOU and number of carbons. That's it. So you can see 1, 2, 3, 4, 5, 6, 7, 8. So number of carbons are 8. And degree of unsaturation is 3 because there are 3 cyclic structures. Next, here you can see 1, 2, 3, 4, 5, 6, 7, 8. So there are 8 carbons, but the degree of unsaturation is 2. So these two cannot be isomers of each other. Got it? Next, here we have 1, 2, 3, 4, 5, 6, 7, 8. So there are 8 carbons, degree of unsaturation is 2. So B and C are definitely isomers of each other. Here carbons are 8, degree of unsaturation. One is a double bond, other one is cyclic, so 2. Yes. So B, C, D are isomers of each other. Okay. Next, notice the 25th one. Which of the molecules are E isomer? Okay. High priority is this one. Here high priority is this one. So that makes opposite, which means E. Next. Here smaller rings will always close faster, so that will be the high priority. Here this side, if you go carbon, 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 carbon. Next atom is oxygen, 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 oxygen. But this side, it is, what do you say? After this oxygen here, it is connected to carbon, while here it is connected to oxygen directly. So which means smaller ring wins here. So therefore, this one is high priority group in this case. So how are they aligned to each other? They are opposite. So that means that is also E. This is also E isomer. Everybody clear? Next. Here, these two are high priority groups. High priority groups are on the same side, which means it is Z isomer. Here, high priority group is here, high priority group is here. They are opposite to each other. That means they are E isomer. So answer is A, B, and D. Everybody clear? Next. Consider the following conformations of 3-aminopropanol against the given conformations PQRS. Okay, most stable one is. And you know that when it comes to stability, it is the gauche form which will try to be more stable because of the hydrogen bonding which it can possess. Okay, so you need to look out for hydrogen bonding where exactly it is present. So check out first. Here there is a hydrogen bonding because this oxygen and hydrogen can make a bonding here. And that's the only form where you can have the hydrogen bonding present. Correct? So yes, the first one is correct. The gauche form is more stable. That is also correct. Anti-form is more stable. Incorrect. Larger groups being separated by maximum distance is the in the conformation. Not necessarily. Okay. So what are the correct options? Only A and B. Which of the following exhibits geometrical isomerism? First, here we can clearly notice cis and trans isomers. Here, this can now in this is decene. In the case of decene, the given structure is cis. Here I can have trans. So yes, this can show cis and trans. Here there is a lone pair, so it is an oxime. It can show cis and trans, syn and anti. Here it cannot show because both sides we have methyl group. So answer is ABC. Okay. In the Newman projection of 2,2-dimethyl butane, X and Y respectively B. Okay. And again, best method is try to draw the Sawhorse projection. That makes it much more simpler to understand. Backside we have methyl and Y group. Here we have X group. Here we have H and H. Now let's compare with the original structure. We have butane with methyl. This is the structure we need to compare. 2,2 dimethyl here. So methyl and methyl. Okay. So now if at all I compare that these two carbons are same, right? These two carbons are same, which means the Y has to be methyl group, correct? And now, if I compare here, these two hydrogens are the ones, then this X has to be this group, which is also methyl. So this X has to be this group, which is also methyl. Okay. So X and Y both should be methyl and methyl. So answer is D. Clear? Okay. Acha. Can it not be hydrogen and C2H5? That can also be an option, right? Because here, if at all I put hydrogen, and see here, let me put it these two like this. If you have hydrogen and methyl, let me show the same structure again. Sorry, like this. Backside I have methyl and Y I'll take it as hydrogen. Okay. No, sorry, not hydrogen. I have to take C2H5. Yeah. If I take this as C2H5 and here I take all hydrogens, so that is still coming out to be the same structure here, because again you have four carbons and here we have methyl and methyl, isn't it? And here we have methyl group. So we can see it is 1, 2, 3, 4 with 2 butyl. So yes, this one also fits perfectly. So B and D are correct. Okay. Now notice how the comprehension will be formed. Find out the suitable substituted cyclohexane among the following. Everybody, whenever you have such cases here, so first draw what is being given. Okay, like this. Correct? And tert butyl is given on the axial position. So do you ever see tert butyl coming on the, because tert butyl is the most bulkiest one. Do you ever see coming on the axial position? No. So that means this has to be probably the least stable conformation. Second one. Here again, this is the chair given. This time it is the tert butyl is given on the equatorial. So that's fair enough. And thereafter methyl is given here. Now we can compare that with the other cases here like this. So here we have tert butyl with methyl group on this direction. So yes, this is even more stable because both of them are in the equatorial direction. Okay. Now again, this is given in axial direction, definitely does not exist. So correct answer is only C. Everybody clear? Next. Notice the next one here. When you have fluorine, if you have a most stable cis form of it, which one is most stable cis form? Okay. And when you have, you know, chair conformation like this, and I have fluorine here in the axial direction, then the next OH here, this has to be like this here. And you know that there could be hydrogen bonding developed in this case. So yes, this can show some stability. Okay. In the second case here, if you have it like this is the axial direction and here it is the equatorial direction like this. So here definitely compared to A and B, A is relatively more stable. And next, In case of C here, if you have it like this, actually this is up and fluorine is here. And you know that when you have axial and equatorial, these two are actually transformed. This is not even a cis form, so this is incorrect. And here also, same thing could happen. OH is here and F is here. This is also a transform. This is trans, this is trans, okay? And this is also trans, sorry. This is cis because fluorine is also here like this, right? So this is also cis and this is cis. So A and B are cis, B and C and D are trans. So since the question is asked about cis form, between these two cis forms here, there is a hydrogen bonding that exists. So that makes it A being more stable. Okay. Next. Compounds which does not exhibit geometrical isomerism. See, diethyl ether. So if you have ether, there is no geometrical isomerism. Correct. A does not show any geometrical isomerism. Next. 2-butene. Yes, it can show cis and trans. Next, 3,4-dimethyl hexene. Okay, so if you have hex 3 in here and 3 and 4 dimethyl 3 hexene. Sorry, not cyclic. Yeah, 1, 2, 3, 4, 5, 6 double bond here like this. So yes, there is a cis and trans existing here. Next, 2-chloro 2-methyl pentene. So here like this, and 2-chloro and 3-methyl pentane. Yes, here also there is geometrical isomer. So only place where there is no geometrical isomerism is A. Which molecule is in E configuration? Here there is no geometrical isomers. So we can rule it out. Here priority wise 1, priority wise 1. So this is Z configuration. Priority wise this is 1, priority wise this is 1. So this is also Z configuration. Priority is 1, priority is 1. So that makes it E configuration. So D. Check out on 32, everybody. Next. Dihedral angle between two methyl groups in N-butane in a gauche form and anti-form respectively are. See, how does the gauche form and anti-form looks like in 2-butane? So if you have methyl hydrogen, here will be methyl, hydrogen. This is the gauche form. And then what is the anti-form? Methyl hydrogen. And here we have hydrogen, and methyl. This is the anti-form. So in the gauche form, the angle is 60 degrees. In anti-form, it is 180 degrees. So 60 and 180. Which among the following conformation of cyclohexane is most stable form? Which one? Share form. Come to the next question. Which of the following shows geometrical isomerism? So out of options A, B, C, D, we need to check geometrical isomerism. Okay, which can show. So now here you have 1, 2, 3. So there are 3 groups, but unfortunately here there are both bromines. Since there are both bromines, it should, this bromine, chlorine, bromine, all of them lie on the same plane, everybody. It is like a pseudo alene. Everyone, Samyag, I guess you understood why it is pseudo alene now, beta. So it is bromine, chlorine. This side we have bromine and bromine. This is how I can write it. It is like a pseudo alene, we can write it. And you know that this is odd number. Odd number will make it planar. And since they are planar, they should exhibit geometrical. Unfortunately, these two groups are same. If they were a different group, they would have shown geometrical isomerism. Now here, these two carbons are chiral as well as they can keep moving around. That means both can be on the same side, both can be opposite. That means cis and trans can be exhibited. So 2B definitely shows. With respect to this double bond, I cannot have any system of geometrical isomerism. And when in a cyclic structure already double bond is there, means it is locked. We cannot have geometrical anymore. So no geometrical isomers here. Now here again, this can be, every spiro can be written as pseudo form. You can see double bond, double bond, double bond. And last carbons have methyl and methyl. So same problem. Instead of methyl and methyl, if you have methyl and hydrogen, this would have shown geometrical isomerism. So even this will not show geometrical isomers. Number of geometrical isomerase compounds in this case are how many? You can see there is no symmetry. So that means this is one stereogenic unit, second stereogenic unit, third stereogenic unit. So 2 raised to power of 3 makes it 8. So 8 geometrical isomers can be observed. Okay, next. Now, given these cases, we need to figure out the highest value is for this one. The second highest value is here. Third highest value, fourth highest, for least value is here. So clearly you can make the highest values for fully eclipsed. So out of this, where is the fully eclipsed form? You can see the third one is fully eclipsed. So P. Next, partially eclipsed. Partially eclipsed is at Q. Okay. Then 3.3 gauche form, which is a gauche form here. So this is 3. So which means R. Okay. And last one, anti-form is 0. So S. So SQPR. SQPR. That is option C. Okay. So it's a very simple one. So I'm sure this confirmation case is clear. Next one. When you have two pi bonds, which means it can show optical isomerism, right? So 2 raised to power of 1 makes it 2. So there are total of number of geometrical isomers is said. So geometrical isomers are 0. So R, answer is R. Now here there is one stereogenic unit, here there is one unit. So 2 raised to power of 2. So total 4 GIs, right? So answer is P. Here you can see 1, 2, 3, odd number and left side, right side, two different groups. So that means cis and trans can be shown. So 2. So next here we have 1, 2, 3. And there is no symmetry because here there is methyl and ethyl different groups. So 2 raised to power of 3, which makes it 8. 8 geometrical isomers. So RPSQ. So that is option B. Next. This molecule and the most stable isomer in the ethane form. See, ethane does not have anti gauche and all of them. They will only have two forms, staggered and eclipsed. So most stable is staggered. Ethylene glycol. Glycol will have more stability because of hydrogen bonding at gauche form. 3-fluoropropanol. 3-fluoropropanol here. C2, C2 and 3. Achha, when you have 2 and 3 here, correct? It is the structure like this. See, let me write the Newman projection for this one like this between 2 and 3. So backside, let's say if there is 3, correct, you will have 3-fluoropropanol. Oh, sorry. It is al. Yeah. So first let me write the structure CH3, CH2, CHO. This is what we have. And here we have uh, fluorine, correct, like this. And you're writing between 2 and 3. So basically on the second position we have two hydrogens and one CHO. And the back position I can have fluorine and two hydrogens. So obviously it can show hydrogen bonding in the gauche form. So which is more stable again? P. P is more stable. Next. N-pentane with C2 and C3. Okay. So C2 and C3 if you have, that will be anti-form because there is no hydrogen bonding here. So RPPQ. So which is option C. Everyone clear? Next. Check out these cases. What about the type of strains we have, dipole moment, melting point, and all of these cases we need to check out. First one. We have OH and OH on this position, gauche position here, correct? So here they are cancelling off with each other like this, but here they are not cancelling off in terms of dipole moment. Okay. So dipole moment wise, R will be, yeah, this based on the structure given, dipole moment is correct here. So R will be definitely matching in this case. Okay, right. Next, in here, if you notice, chlorine and chlorine here, dipole moment is also more as well as.
So what's that blue here?
Okay, R is matching here.
What's that blue here?
Okay. Once again, sorry. Yeah. And along with that, you know that when it comes to melting point, trans would be more than cis. So 2 is not matching. And here, this is a, I mean, torsional strain wise, eclipse will have more than uh, staggered. So yes, P is matching here. Okay. Next, boiling point, it is matching even for cis and trans. So 2, I mean, this S is correct here because cis will have more boiling point. Okay. Uh, and last one. Here, trans is greater than cis. That is best possible when it is at a melting point case. So yeah. So check out which one has these options which are more appropriate. R, RS, P, and Q. Yeah. So I think the D one is the more appropriate match. Let's check it out. Clear? Any doubts there?